For those of you who have joined us over the past few days, you'll already know Andreas as the CEO of Math2Market, which is a software company in Kaiserslautern in Germany. Is that pronounced correctly?
Kaiserslautern, yeah.
And this is spun off from the Fraunhofer Institute back in 2011. Dr. Wiegmann's work on random 3D material models and image-based material property computations ultimately led to the creation of GeoDict, which is the main flagship project of Math2Market, and it's a digital material laboratory. So over to you, Andreas, and as before, could you please add questions to the chat, and we'll field these to Andreas at the end. Thank you.
Great, thank you, Leon, for the introduction, and thank you all for attending my lecture today. I was impressed by the previous one and the use of AI and machine learning. Fortunately, it's in my presentation as well. I have way too many slides, and so I'm able to pick based on the previous one, maybe to follow up on some hot topics there. Yeah, GeoDict, an integrated environment for image-based simulation and design of materials and processes. Yeah, naturally, we as being the CEO of Math2Market, I speak about our product and what we can do. And I'll get into that at first by saying a little bit about, we're not just Math2Market, we have partners around the globe by now that help us get in touch with even more people than we could do based in Germany here as we are right now. We have about 170 clients total. There are some big name companies right there. On the top left, you see Shell or Toyota, Volkswagen, and BASF, to name some commercial ones, or famous universities or institutes like NASA or ETH or RWTH in Aachen and so on. And yeah, unfortunately, not everybody allows us to list their logo, and we haven't asked everybody, so that list is growing as we make progress. Our services, we really provide consulting projects involving micro-CT, synchrotron, and FIB-SEM scans. Those projects often are setting up a material design workflow. This is what the software is originally intended to not only work on images, but to generate artificial images and find materials or find procedures that work actually better than what exists in reality. But everything starts with the images of existing materials typically, and then we end up modifying those. We do software customization, software development, video tutorials, regular printed tutorials, online seminars, workshops, like we did the last couple of days. And many times our clients, as they are usually doing research, both academically or in industry, are interested in publications in scientific journals or joint presentations at technical meetings as well. So being at a meeting like this one is not so uncommon for people from Math2Market. We provide solutions for 5 different areas. Let me start with the newest edition, which is the image processing and image analysis one. It's really not that new. We just realized that we need to bring in the synergies from images coming in from actually the other 4 and many more applications, and the knowledge of what is done on the images initially is now focused in one of our groups, and the other 4 are actually application areas where some specific aspects of image processing and image analysis cannot be have more importance maybe than other ones. So we started out historically at Fraunhofer with filtration. Then we added a lot of electrochemistry where fuel cells and batteries are of interest. Later on, we added structural materials, we call it now. It was composites. You can see some of the images there. There's also some foams, for example, that we call structural materials. And the latest edition, but by now that's already 7 years ago, we got into digital rock physics. So many 3D images are taken also of core samples and then analyzed. And they are clearly, there's no design of the digital rock, but you are interested in changing processes. So for example, two-phase flow in the rock, you might add some chemistry and change surface tension, things like that. The company has grown from 0 actually, which we didn't draw that on the left side when we started in 2011, to by now a bit more than 40 people. We had some pretty good growth rate of about 25% of accumulated annual growth rate. And then we paused for a couple of years. And fortunately now even in spite of COVID-19, we're doing okay. And we're actually back into growth mode now. And in fact, we're hiring. So if there's anybody in the audience that knows a process engineer with an interest in business development, that's what we need. And maybe a master's degree or an experience or a PhD in that field. We're looking, and there's a job offer on our webpage. So GeoDict in a nutshell, there are 7 things that we also listed in the workshop the last couple of days. The first thing we start out with, definitely here in the image-based simulation regime that's talked here, is we import MicroCT, FIB-SEM, or synchrotron scans, and we can process, segment, and label them, etc. So once you have that scan in memory, you can analyze it for what we call the geometric properties. For example, porosity, pore size distributions, fiber diameters, fiber orientation, etc. And with that information, you can feed stochastic models to generate artificial 3D scans for considering all the properties that were analyzed in the previous bullet, but then also things like representative elementary volume. Yeah, is the domain large enough so that what you compute on it later will have a chance to agree with experiments? There is the competing factor of the resolution, right? Ideally, you have infinite resolution, very, very small voxels, and a very large domain. And then you have that problem of size, and the quest for speed was already mentioned in the previous talk. Yeah, you have that, and so that limits somehow what sizes you can still work on. We try to work on as large as possible. Yeah, both on the images, the original scans, or on the artificially generated ones, we can simulate processes and predict, for example, effective material properties such as stiffness, diffusivity, permeability, conductivity, etc. Or as processes go, we can even compute large deformations, and every deformation step will get a new image out there. It's really completely image based what we do. Every computational mesh that we're setting up is another image. Might be rediscretizing some analytic objects, or you really have to move voxels around, etc. There are things like battery charging, where if you have damage, then that will change the geometry as well, or filter lifetime, where a filter will clog with particles and the particles change the flow, etc. And we do all this internally. The data structure is really 3D images, let's call it, voxelized meshes for computations. So both the structural data, yeah, so geometric information, and the fields, we call it, like a velocity field or pressure or concentration, things like that, they can be visualized and post-processed. And not just with our software, but we have interfaces to Python, Excel, MATLAB, etc. And you can prepare presentations even automatically with PowerPoint. Now here is one. We'll see a few of the things that come out of the software later. And all of the above really can also be automated. Yeah, so you need to set up workflows, in particular if you work with industry, that are repeatable, and you need to do the same thing over and over again, either for design of something, or if you have a core analysis, you need to not have to have a person sitting in front of the software, but it all needs to be done by scripting, and that's possible with our software as well. So now I'll get into the probably more interesting stuff, some examples of what we do. For example, if you're familiar with FIB-SEM, there's a typical number of artifacts in there, and I'll get into learning these and AI later also. So there's image alignment or curtaining, which we see in the animation on the bottom left there. There's changes in color because the object is in a diagonal in the scan. There's local charging leads, etc. So there's non-invaded pores after resin infiltration. So FIB-SEM has a number of artifacts that need to be corrected. Here's one example of how one can align a stack of FIB-SEM images that's on the left, actually jumping around or moving around, and on the right they're all aligned with to be always in the same position. And you see this black line coming up here at the bottom, where there was no image there, but the motion of the original stack has led to that black line moving in. Or here we have a sequence 2D slices through a NANO-CT image, and we see some flickering as it's animated. The right one has that flickering on it. That's also illustrated with the graph on the right. Yeah, so the mean value of the gray values, that's the peak that you see on the right there, that is actually moving as we're moving through the slices. And that is just an artifact, and that can hurt you when you're doing threshold-based segmentation, for example. And so on the left, we have actually aligned all this for the proper graph. Actually, now that I talk about it, we should maybe have the graph for the left image showing as well. You will still have some variation in height, clearly, as they are, not all the images are the same, but the center gets aligned in the middle, for example. Here's one. Oops, that doesn't automate by the start directly. Here it is. So the curtaining, the artifacts that you see on the left image there can be removed by doing an appropriate filter, and you don't do this just on one image. You have to do it on the whole sequence of images. So just a few examples of what you might want to do in image processing with 3D data sets in order to then do further analysis, either identify the different phases in the image, or even further do some computations after that identification. So there is this huge topic of machine learning in changing really everything that mankind does. In the previous talk, it was manufacturing, and definitely machine learning has huge potential in image-based simulation as well. And what we see here is some project work that is illustrated even by the title slide, done by Math2Market in combination with Bruker MicroCT, who provided the very large scan that we'll talk about in a moment. And in that scan, you see up here a red fiber and a blue fiber identified. Here's the red, there's the blue. Yeah, so out of this three-dimensional voxel data set, fibers were classified as individual objects and then measured for length and diameter and stuff like that, for example. So here's here's our approach to doing this kind of work. So with what I mentioned earlier, we have the possibility to generate 3D models. Yeah, so very similar to the previous talk, our training data for the machine learning algorithms are computer generated. And up here we have an example of 10 digital siblings with a variation of fiber curvature, orientation, length, and diameter. And so this corresponds to about 1 billion training data points for the way we're doing it individually inside the algorithms. And the main point, and that's why they're in color, we actually have the information about the individual fibers, right? So this is already voxelized, but the voxels get different colors depending on what fiber they are in. So that's really the result that we want the AI to come up with. So this is the ground truth. And then it's actually very easy to create segmented artificial scans by just changing them to black and white, right? So now we only have solids and empties, and that's very similar, and they should look very similar to your real scans that you want to segment. We have just black and white images, and for those we have the ground truth, right? So this can then enter into the training algorithms. So we feed not just one, but a bunch of them to have enough data. And in the initial training phase of the neural network, yeah, we have it symbolized in here. So both the nodes and the values at the nodes and on the edges will have to be modified. So the neural network kind of learns its parameters in the center here from having given the ground truth, you know, which voxels belong to the same fiber roughly, and the binarized input on the left there. And then actually in the usage phase, these arrows here, they change direction, right? In the usage phase, the input data, and here is this very large data set, one of them given on the left, and it gets fed into the neural network, and the weights on the edges and the weights on the nodes have been learned before. And then the neural network, or by machine learning, we label the individual fibers on the 3D scan. Yeah, so in a nutshell, you can use the same graph for the training phase when the left and right determine what's going on in the middle. And in the usage phase, the left and middle actually determined on the right, and you get to identify the individual fibers. So here's what happened here. We received a non-woven sample, and it was rather large. You see that the imaging made it in one direction, about 18,000 points by close to 5,000 by close to 2,000 points. So that's actually 150 gigavoxels. Bruker had to use a stitching technique of taking multiple images. I think there were 4 or 5 in one direction, and stitching them together, and then deliver that to us. And we segmented it and analyzed the whole thing. And there are 2 samples in this particular presentation. We can do a virtual SEM representation of a micro-CT scan here to have a given impression what this looks like. And we have it from the top view where the fibers are oriented in the XY plane in this image. And then we have a cross-sectional view in the other directions. Resolution was 2.4 micron, physical dimensions 44 by 12 by 4 millimeters roughly. Same thing for the second image. You can see why one would want to do this. You have 2 different types of materials, and you really want to see after analysis, you know, what is it that's different about them? Yeah, not just porosity, which you might still get with other techniques, but fiber lengths, fiber orientations, fiber curl, etc., all of that. So we have here a visualization of these 3D scans. There are clearly 18,000 voxels in the X direction here. Cannot be rendered on the screen. Yeah, mine here has about 2,000 voxels in the horizontal. So we have about 10 times higher resolution than one can even visualize there. But it still gives a good impression of the sheer size of these data sets that were handled. And I have to admit, the guys, yes, we do have very, very good computer scientists on staff that do this kind of work, again, agreeing with the previous speaker. These things require about a terabyte of memory to do the whole analysis, including the rendering, for example, as well, which is a good workstation, a really good workstation that we have in-house at Math2Market. If you want to go bigger, then at that point, you're going to have to go to up to 6 terabytes is available now still on workstations. And only past that would you need to go to cluster computing in our case. Yeah, we do everything on desktop machines still, or on definitely affordable workstations, maybe up to, I guess, 15,000 euros or so is one of those computers. Once you have that information, you can get fiber orientations for both samples. And then here we're illustrating just a cutout. You see all the individual fibers found, or here you have one of those fibers that is known. And once you have the individual fibers, you can get their length, curvature, and other properties with fairly straightforward, well-known algorithms that are standard. The AI helps you to get the objects then with which then you can do more work. So this is a piece of the talk that I pulled up just as I was listening to the other guy, the previous speaker. What was not good about the previous method of doing machine learning is we had segmented the fibers beforehand, and so the segmentation step can produce a lot of errors, and one would really want to work on machine learning for the original gray value image, and we are working on that. So we need to create artificial micro-CT scans. Yeah? So rather than what we see on the top here, just red, yellow, and green phases and maybe pores in between, we really need to have gray values that correspond better to what comes out of a micro-CT or synchrotron or FIB-SEM. And so we started working, and the guy that's doing most of the work here is actually Andreas Wiegmann, as there were other people doing the work on the previous topic as well. Yeah, I guess I'm paying the paychecks, stuff like that. So I give contributions to advising on ideas and so on. The 3D data sets, yeah, that we're producing from our stochastic models look like the colorful one on the top, and we really need to go to something that's towards the right there in gray values. Why do we need them? Well, the bottom says right there, artificial intelligence learning materials, yeah, to do the stuff with the previous set of data, fiber identification without needing to segment first. But one really needs these also to improve your own image processing algorithms. That's what we started out with originally. Yeah, you have all your filters and your segmentation algorithms, and you need ground truth to get the quality of those algorithms as well. Yeah, it shouldn't be always just people. So there's multiple uses for artificial scans, and we're not the only ones doing them. And here's an example how they could work. Yeah, we have an original scan on the left, and it's segmented in the middle. That's actually from some rocks from a core plot, just one slice. And for something like this, one can see also by the eye how good your artificial micro-CT scan can be. Yeah, so the image on the right is created from the image in the middle, and is supposed to look very close again to the one on the left. And we can see some places where the coloring is not exactly the same, but it's the thing on the right looks like a somewhat filtered original micro-CT scan already, maybe. So how does one do this? Well, there are a number of different effects that one needs to add to the original computer-generated model that was in there. For example, edge brightening in SEM or FIB-SEM images. Yeah, so that would look like this. Around the edges, you have these brighter lines there. And one can add that as with a technique that's based on distance transforms. There's an extended version of the slide deck that explains that better. There's noise on the images, so the untreated image looks like that on the top. Then Gaussian blur, Gaussian random fields is one technique that we add noise with. And then we have on the bottom normal distributed noise. So you can pick your noise level, and then again we have slices through the computer generated image. That's all that colorful one originally, now with the right colors where noise has gotten into it. You might want to introduce brightness artifacts, so there's a lighter and darker areas in this image that were added afterwards. You can have overexposure, you have very light a particular binder in this case, or there may be flickering. That's the one thing we created, we removed from the NANO-CT earlier. You have misalignment in FIB-SEMs again in particular, where the individual frames jump around, or you may need to remove ring artifacts and so on. And so your AI should be trained on images with all these artifacts on them to then recover what we had started out with in this process. In our case, the model, but if a real image goes in there, the real objects that were segmented into, here, two kinds of binder and fibers, let's say. So this is one of the topics that we provide other people to work with as well. Another topic, additive manufacturing, that fits rather well with the previous talk as well, as that 3D printing or additive manufacturing was mentioned there also. We give here a very brief example of a collaboration with two more institutes in Kaiserslautern, the Institute for Composite Materials and Fraunhofer Institute for Industrial Mathematics, where there was an example looked at of a metamaterial that behaves very differently in two different directions. And I'll actually show you that behavior down here. Yeah, so as you press on it from the top, initially, there is very little stress in the objects until the thing has folded and the things start touching each other, and then there's a very, very steep increase on that. And this was actually simulated on like a CAD drawing, a 3D drawing of the thing with our software that can also do mechanical simulations. So then the data were also given to a 3D printer. Yeah, so that's symbolized here. And then that object was actually existed in reality. And then some measurements were done by the Institute for Composite Materials, and the measurements on the real part didn't match with the model ones that we see here also in blue. So that's what you don't want to happen, right? You really need to, and here's the illustration of what the two ways are. Yeah, so we had a CAD model, we had this unrealistic model part, we simulated some behavior, and then we also went to STL, gave it to the printer creates G-code, a physical part came out, and on that we measure something else. So that discrepancy is not desirable. Yeah, you want to design in the computer and know already the real properties that will come out when you are designing it beforehand, and you don't want to be off by that much as we were in these simulations. So that inequality had to be studied, and yeah, here's a little bit of the story. So the real specimen that you see here on the left was placed in the micro-CT scanner. Those data were imported again into GeoDict, and then on the segmented data, we also ran simulations. And you see the two of them, the idealized model and the micro-CT data, they differ significantly in that the printer has left quite a bit of pores in the model, and maybe here it's a bit exaggerated to show. Yeah, you wouldn't probably leave that much porosity in anything you do for real. So then the sample was also placed in a measurement device at IVW to do digital image correlation, and the colors were chosen to be the same as in our simulations there. And this is a top view of the 3D specimen on the left, and in the right, that's one of the cross sections there through the simulation. And what's interesting is not only is the shape very close, but also the strains that can be shown by digital image correlation, they're also in the right places, and the orders of magnitude, I think, are okay there as well. So you really learned something about the compression behavior in reality on the left with the experiment, and also with by using the simulation. And yeah, lo and behold, when you do the simulations on the micro-CT scan, then the curve of how the material behaves is actually very similar to the experimental one. So here we see the gap. Yeah, so our cut model doesn't take into account all the artificial printing, the changes to the real object that come in by the printing process. And so then here, at this point, instead of going through the G code and to the 3D printer and then creating the physical part, the guys at Math2Market, and Rolf is in the audience here, it was, I think, his particular idea and implementation. From G code, we actually creating an artificial 3D scan that looks just like the printed scan and has in particular all the pores in it. Yeah, and so there you come up with a realistic virtually printed part. Yeah, and here's the visualization of that. So here's the micro-CT. Yeah, when you actually run the G code and you're creating the individual, yeah, let me call them sausages or something, you know, that lead to the pores in between. When you do the simulations on that computer-generated 3D printing process after the cut model, then that matches very well also. And that's the story right there. So to get the 3D objects right, you have to have the process modeled correctly as well. And in our case, we actually, the output of our 3D printing is again a 3-dimensional image, as all our modeling is done as 3D images. And on that, we can just naturally do the simulation again. It doesn't matter if it's a micro-CT, the idealized cut, or if it's an image that shows the effect in 3D after the printing process. So the curves agreed. We were very happy to see that. Cleon, how much time do I have left?
We started
pretty much, right?
10 minutes late, so you've got 5 minutes and then 5 for questions, if that's okay.
Okay. Great. Yeah, give me 5, and I hopefully have some interesting things that make it worth your while. So here's one. As we were looking at mechanics before, another example of mechanics. So here we have a foam structure. This one is computer generated with our foam modeling software, but you could take a scan of a real material, and as I don't get to saying that much about it elsewhere now, for that material, you need to have what's called a statistical digital twin. Yeah, so generate a structure with foam geo that is statistically proper, has the right pore size distribution, right walls, you know, right everything. You need to get the behavior right. Besides the image, you also need to identify the different materials in that image, not just solid empty, and you need to know the constituent material properties. So somehow into this simulation went also what's called a material law. How does the particular, I think it's some kind of polyamide or something, how does the particular material behave? That gets entered into the simulation, and then we do these large deformations here, and we get the curve here developing that was animated before with the 3D here, and that behaves just like theory says for such kind of foams. And to my knowledge, we're the the only supplier that can do this kind of very large deformation. You know, we're squeezing out 80% of the volume there without the software crashing. Yeah, we don't need to do, we do need to do some remeshing, but it's done automatically, right? You revoxelize the individual steps right there. Yeah, we have some partners that tell us we're the only ones that can go this far with compressional foams, let's say. There's these theory stages. There's a little bit more of foam compression right here, for example. And I'll go to the show also the effect of putting some tension on a different object here. That's possible as well. Yeah, compression and tension have different difficulties. Yeah, under compression, objects will start touching each other and you need to detect new contexts. And under elongation, things will get a lot thinner and you may not have enough resolution to still keep a wall resolved at this point. And so both of those have their individual difficulties. So as I know there's somebody in the audience that is interested in ceramics and filtration, I'll go into some filtration modeling here, where we have for ceramics 2D images available and then models. A lot of work went into that. And then first one checks that the models and the real data, the simulation and measurements actually agree. And then after that, there's a filtration process. I'm showing this because I promised it basically in the session on Monday that we were going to get into this. On the right, we see a ceramic. We don't visualize the flow through there, but what you do see is there is actually soot being flown in from the top, and we see what's called filter cake growing on top of the ceramic there. And we see also the soot forming in the pores. Yeah, so there's a big cutout here, so we can see some of the soot also inside the material as it is developing over time. I'll start the animation again. And here on the left, you have, there should be like an exponential curve ultimately of how deep has soot entered. And after a while, no more soot can reach down here. Yeah, and that curve stabilizes. And later on, the soot is building up here on the cake now. Now we're on top of the ceramic, and there's still, yeah, there's no more soot entering into the ceramic here at this point. The curve is not changing. So yeah, after that, let me go to the conclusion here. And finish, hopefully, reasonably well in time. So I didn't get to the topics, not to all the topics. I thought machine learning was maybe the hottest one you'd be interested in. We do this for fuel cells, batteries, after treatment catalysts. For all of those, the microstructure of the material has a huge influence on the performance. And people are realizing for the last decades, I must say by now, using first synchrotron, that you need to study more and more detail to get things right on the macroscopic scales. Yeah? So on the part scale, you need to know how the constituents behaves, what's going on in the details. And this is our regime where we are doing the imaging, the modeling, and then the geometric modeling and process modeling. So the characterization of materials can be done by experiments in reality, and we are doing that on images. Yeah, the dream is to ultimately you can replace all your experiments by just taking a 3D image and then run the simulations on it. Yeah, clearly that's a far-fetched dream, but in many areas we're making good progress. So transport, diffusion, conduction, stiffness, deformation. You take an image and you simulate, should agree with what your real experiment tells you. And when we have reached that, then you can make modifications on the images and do the design on those images. So by screening designs digitally, new next generation materials can be found more quickly than they get done by real trial and error. Or you can try many more cases in the same time than you could by making real prototypes. And actually, all this can be done with our easy to use, highly efficient, well documented software. There's about 1,400 pages of user guide, for example, that tell you how to do all this that I've shown yourself. Let me advertise, if you want to know more, we have our user meeting coming up 2 weeks from now. It's open to the public. Check out our webpage if you are interested to learn more about one of the topics. You don't need to attend the whole thing. It's 5 days with different priorities on the different days, and maybe one of those is interesting to you. There's also workshops for those that want to get their hands on using the software during that period. So there was a lot of work shown here by me, and I stand on the shoulders of giants. That's the Math2Market team that, well, we have some more people, and a couple of people have left since that video was taken, but pretty much those people were all very helpful in doing this. And I thank you for paying attention to my lecture. And let me point out one more time, next generation materials with GeoDict. Yeah, we help you define them faster, and I'm happy to hear or read your questions now. Thank you very much.
Thank you very much, Andreas. So we're running a bit behind, my fault, but we will take a few questions. So if you could add those to the text chat, then I'll forward them to Andreas. So we have one from Oksana. How do you estimate material properties for filtration?
Very good one. The filtration is one of a couple of the worst topics that you can be on. So we're doing filtration on the micro scale, so we're interested on the actual filter media, and only in the longer run, and now we have moved also to the complete filter. So let's focus on what's called flat sheet media or just the filter media. So there are several steps there. You need to have a geometric model for the filter media. So for example, an oil filter is often made of glass fibers or cellulose fibers. So you can take a 3D scan of that or model that. Then the second ingredient is the fluid that goes through that filter. It could be the liquid or gas. Let's say for the soot example that we had earlier, that would be air that flows through that ceramic. And so the first thing that you do, not even for the filter, you check that the pressure drop that you get for a given flow rate, yeah, the air moves through the, and I could share that, that slide probably again. Let me see. The air moves through the filter, and usually there's a, hang on, wrong PowerPoint. Automotive clean air. So now I think you see that animation again that I showed earlier. So there's the air that moves through this. So the first thing is that for the given flow velocity or given flow rate, the pressure drop that you are getting out of the air moving through this filter here should agree with what you're measuring. Just a clean filter measurement has to work. And when that fits, then you think, wow, I have a good geometry model for the red ceramic grains here, for example. And then, so after the structure model and the flow of the fluid through there, then we're adding, in this case, it's soot particles, but you can add various kinds of other materials. Soot I actually like very much because we know that soot is very sticky. So from a simulation standpoint, at least you don't need to worry. You know, wherever it touches, it will stay on those surfaces. Yeah, and for other kinds of particles, you have them bouncing off again, or sometimes they stick, sometimes they don't, and then you need to model that, and you have additional parameters. So then you have to model the motion of the particles with the fluid. Yeah, and we have all kinds of effects, like very small particles can even have random motion to them. Once they are below a couple of microns, then random motion will start a roll. They will not just go with the streamlines, for example. Or if they're large particles, they have inertia. So those particles are being tracked with the flow, and then when they collide with the red parts in this image, with the grains, then you have to make a decision. And as I said, soot will just stick, and that's great. And other things may bounce off and go deeper. And so the soot that went all the way down here and is visualized here, it means it has traveled in early stages of the simulation all the way down here to then only finally get trapped by touching one of those grains here very close to the outlet. It almost made it out there. This was in the initial phases, and you will have some now I don't know the word in English, at the very beginning in filtration, many times you have a little bit of particles going through and later everything gets filtered. So in a nutshell, it's complicated, and we have to do multiple things: the material model, the flow model, and then the particle motion and the particle capturing. and iterate on it. Maybe I should say that also. Yeah. So we do this by, this were about 150 or so flow simulations. Yeah. So we simulate the flow, we track a bunch of the suit, and then the flow field changes, right? So the suit actually becomes a porous media here. Up here, it's very obvious. So this has a, is not resolved by the grid anymore and gets a what's called flow resistivity that has to be modeled right. Yeah, and so the flow still goes through the captured suit up here, because that's a porous media that's being formed, and then there's porous media forming in the pores in here that allows flow through it, and you have to model how particles may get captured also in the porous media or not. So yeah, it's one of the, we have several, but this is one of the more complicated processes on which you might want to do a design. So how would the design work? Well, you see how this works, and then you're changing the, say, grain size, or you're creating a gradient in here, or usually there's a wash coat on top, so you change the top layer here, and you see in the computer how much soot gets trapped on the bottom, what's the flow resistivity, etc. during the simulation. Good question. You gave me a chance for a long answer. Yeah.
Great. So questions have been coming in thick and fast, but Rolf, fair play to him, has been answering them in the text chat. There's one more here. Hi, Andreas, from Tristan Lowe from Manchester. Hi, Andreas, really enjoyed your presentation. During in situ compression of foams, I've usually seen a sharp drop in the load when the main cell walls collapse, followed by the usual increase due to densification. I didn't see this in your graph, and I was wondering if you took this into account.
I think that this could happen maybe if you're using aluminum foams, or I'm not sure. Yeah, I'm not the expert on this here myself. So that would be my question back. What was the constituent that we're putting in there? If it's polyurethane, or if it's an aluminum foam, which is used in cooling applications or in like in crash simulations, etc. That that could have an effect in that direction. And so we would need to see if my explanation is right, and if we, when we put in the different material parameters for a metal, for example, we would get that different kind of behavior that you mentioned.
Yeah, so Tristan has replied, yes, it was aluminium.
Yeah, so that's, yeah, so then the constituent material can lead to different behavior there, yeah. And then and I agree, we should also run an aluminum foam and see if we get the behavior that you're observing. Yeah.
Great, thank you.